Welcome. Let's take a quiet walk into the kind of strangeness that makes the night sky feel wider and home feel closer. We'll listen for a rhythm that seems to travel without travelling at all. Give me 32 seconds and you'll see how entanglement differs from a hidden pair of gloves and how a small twist of the detectors proves it. Two boxes with gloves only ever match because they started that way. Rotate your checks and the matches stay ordinary. Entangled photons, though, keep a deeper harmony when you tilt the tests. There's one catch. Those tilts matter in a very particular way. We'll return to it. They look like ordinary dots of light. A pair of photons born together rush apart like duet partners leaving opposite wings of a stage. If you watch one, the other seems untouched. If you watch both, a pattern appears, like two instruments that never miss a beat, even across a silent hall. The usual story goes like this. Perhaps the players agreed on the tune backstage. That would be the glove-in-box idea. Each box contains a left or right glove fixed from the start, and opening one just reveals what was already true. In physics, that backstage agreement is called a hidden variable. But when we start to rotate our measurements, turning the musical score from one key to another, the glove story frays. Entanglement keeps time through those changes in a way that no pre-written part can match. Imagine each photon as a tiny violin, with its note measured by a polarizer instead of an ear. We can set our polarizers at any angle, like turning the page to a new key. When both polarizers point the same way, the notes agree perfectly. When we choose different angles, the agreement fades, but not like ordinary coincidence. It fades with a signature curve, a kind of soft crescendo and diminuendo that refuses any simple hidden plan. This is the first hint that we're hearing a different sort of music. Not a signal, not a whisper sent across the gap, but a shared score that only reveals itself when the two parts are compared. You can sit with one violin and it will sound perfectly random. Only by listening to both do you hear the duet. There's a second catch we'll meet shortly. How can such a duet avoid sending messages faster than light? If this brought you a little calm, feel free to like and subscribe, and tell us where you're listening from and what time it is there. Entanglement, then, is the name we give to correlations that resist the glove story, that keep their harmony when we tilt the stage. To feel it fully, we'll need to pick up those polarizers and turn them carefully. Here's the promised turn of the wrist. Place a polarizer at your station, I'll place one at mine. We don't coordinate, we just choose angles, sometimes the same, often skewed. When the angles match, our notes agree every time. When they differ by a quarter turn, our notes dance in step about half the time. In between, the agreement follows a sinuous bend that hidden variables never quite reproduce. John Bell distilled this tension into a test, like asking whether two musicians could fake a perfect jazz conversation using only fixed cue cards. The cards, local hidden variables, can't cover every twist we throw. Bell's inequality is that boundary. Experiments sing across it. By choosing detector angles after the photons are already on their way, and by changing them quickly and randomly, we've watched the duet land on beats no stack of cue cards can guarantee. That's loop A paid. The tilts matter because they reveal the angle-dependent harmony classical plans can't mimic. But another question rises with the applause. If the notes line up so neatly, could one photon be messaging the other? The speed of light is the pace setter of the universe. Can a duet outrun it? There's a catch there too, and it's subtle. We'll open it now and return in a moment. How can perfect correlation coexist with perfect local randomness? The experiments are meticulous. We separate detectors by kilometers, add timing windows, randomize angles with cosmic noise, and still the pattern holds. The shape of those correlations, stronger at some angles, weaker at others, matches quantum theory's score, not the gloves. It's not that the universe cheats. It simply plays a different game, one where what is depends on how you listen. To keep our metaphor honest, there is no string between the violins. There is instead a shared composition that only gains its notes at the moment of measurement, and yet has been prepared so that the notes will harmonize if asked in matching keys. In a few steps, we'll see why this doesn't send messages, and why your violin alone will never reveal the duet. Let's settle the messaging worry. Sit with your violin, your photon, alone. No matter what angle you choose, your outcomes are as random as rain on a window. The distribution never changes when the far detector turns. That's the first rule. Entanglement gives correlation without control. You can't use it to send a whisper faster than light because you can't choose the note your instrument will play. Only when we bring our logs together, comparing timestamps like bars in a score, does the harmony appear. That comparison can't happen until a signal crosses the space between us at most, light speed. So the duet respects the tempo of relativity. It's as if the score keeps two parts locally noisy but globally arranged. A tapestry whose pattern only shows at a distance, once the threads are laid side by side. What then is created at the moment of measurement? Our metaphor says a note, physics says an outcome. The two are welded by a rule that ties the outcomes across distance, but only when we ask corresponding questions. That tie is laid down when the pair is prepared, not later transmitted. The pair leaves the source like two halves of a single chord, waiting for listeners. Now a new question peeks in, quietly. If a shared score can't be used to send messages, can we still bottle it, move it, spend it? Entanglement, it turns out, behaves like a resource, fragile, distillable, and convertible into tasks. We'll open that door gently because first we need to know how such a delicate harmony survives the hiss and shuffle of the world. Noise is the soft chatter of the audience, and entanglement is the whispering duet. The world is full of aircon and raincoats and coughs, thermal motion, stray photons, jostling atoms. When the environment touches our instruments, it learns a little about the notes. That knowledge leaks the music away. We call the process decoherence, the erosion of delicate quantum phases as the surroundings eavesdrop. You can feel it through an everyday lens. A quiet pub turned busy blurs the conversation at your table. The meaning is still there between you, but it's drowned beneath other voices. For quantum states, the murmur is physical. The more bodies bumping into your particles, the faster the duet loses its edge. Entanglement spreads to the room, to the walls, to the air, and what was once a crisp two-part harmony becomes a diffuse chorus, useless for precise work. We fight back with careful staging. We cool things to near absolute zero so the air grows still. We align fibers, isolate crystals, time our measurements to beat the drum of noise. We also learn to shape the songs themselves. Some states are robust, others fragile. Bell pairs are bright and brittle. Cluster states can be stitched and restitched. Squeeze states tuck their vulnerability into quieter quadratures. This is the craft of keeping a hush in a busy hall. Now we circle to that resource door we cracked open. If entanglement can be spoiled, can it be purified? Yes. With the right set of filters, local operations and classical messages, we can take several noisy duets and distill a smaller number of cleaner ones. Like taking many grainy recordings and editing together a single clear track, the shared harmony can be rescued, at a cost. Once you see entanglement as a currency of coordination, a trick occurs to you. Could we use a shared duet to send a state without sending the physical object? Quantum teleportation is the answer, and it's less science fiction than smart accounting. You and I share a pair of entangled photons, our blank duet. I hold a third photon whose note I want you to have. I perform a joint measurement on my two, asking a question with 4 possible answers. Each answer tells me how my unknown note entwines with our shared chord. I send you, over an ordinary channel, 2 classical bits, the index of my answer. Those bits travel at or below light speed. When they arrive, you adjust your photon by a small prescribed twist. The result: your photon now carries the note my third one had. Mine has been spent. The original state is gone. It is not copying because quantum notes resist cloning. It is transfer by choreography. Entanglement plus 2 bits of instruction. Teleportation is real and routine in labs, across fibers, through free space, aboard satellites. It's a quiet marvel of the duet, proof that shared harmony can be cashed in to move a melody without moving an instrument. This power has a break built in. The duet can't be split endlessly. You can't keep my note and give it to someone else. You can't teleport without those 2 classical bits. The universe keeps its tempo. Nothing leaps ahead of the light. Scarcity sharpens value. Entanglement is monogamous in a way ordinary correlations are not. If 2 instruments share a perfect duet, a third can't be equally bound into that same pattern. There's only so much coherence to go around. The more deeply 2 are entangled, the less room remains for others. It's a rule with teeth in our craft and comfort in our security. Think of it like this. a tightrope meant for 2 sags and snaps if a crowd climbs on. In practice, this means that if you and I share a strong entangled pair, an eavesdropper can't be equally entangled with us. Any attempt to latch on changes the tune, introducing errors we can detect. That's the backbone of quantum cryptography, not secrecy by complexity, but secrecy by physics itself. This monogamy also shapes computing architectures. We can't spray perfect entanglement across every qubit without consequence. We must route and ration, building lattices and chains where the harmony can be moved, stretched, and reknotted. In doing so, we learn to think like conductors of a delicate orchestra, not hoarders of a bottomless stock. There's a fresh doorway here. If entanglement grants unforgeable coordination, how can we use it to guard our words in the wild? A protocol called QKD will let us listen for the slightest sour note from an eavesdropper and abandon the track if the duet is spoiled. Let's step into that practice. In quantum key distribution, we don't lock the door after the burglary. We aim to make theft impossible without noise. We share many pairs of photons, choose measurement angles randomly, and later compare a fraction of our results. If the correlations we see are strong enough, entangled enough, we can quantify how much information an eavesdropper could have gleaned. If it's too high, we simply throw the session away. 2 flavors matter. In prepare and measure, one of us sends single photons in varied polarizations. In entanglement-based schemes, the source spits out pairs like twin notes. The latter can be made device-independent, secured by the violation of a Bell inequality itself. No need to trust every screw in the detector. If the duet sings beyond the classical boundary, security follows from that song. It sounds like magic, but it's bookkeeping. Classical communication accompanies the quantum, guiding error correction and privacy amplification, the polishing steps that turn a noisy shared string of bits into a short, clean secret key. Cities now string these systems along fiber webs. Satellites write them across the sky. The music of entanglement leaves the lab, step by careful step. The turn ahead is subtle and deep. If we can spend and save entanglement, can we measure it as cleanly as we measure energy or time? How do we know how much duet we really have? That's our next question. To treat entanglement as a resource, we craft yardsticks. Some look at how hard it is to assemble a state from scratch. Others ask how many tidy bell pairs we can distill from a messy choir. Entanglement entropy, concurrence, negativity, each a different way to weigh the shared note in a state without peeking at any secret backstage. These measures have a common pulse. They don't grow when we act locally and talk classically, because that's not where the magic lives. Only by joining subsystems in quantum ways, letting their phases braid, can the weight of entanglement rise. Resource theories formalize this: allowed moves, forbidden conjuring, costs tracked like coins. In many body systems, something beautiful emerges. Ground states of gapped materials obey area laws. The entanglement between a region and its outside grows with the size of the boundary, not the bulk. It's as if the harmony accumulates along the shoreline of a sea, not in the depths. This geometry guides our algorithms and gives us compressed descriptions, tensor networks like cords that tie the music into manageable braids. But a question stalks the wings. What, if anything, is really happening between the measurements? Do we collapse notes as we listen? Do all branches play at once? Is there a hidden drummer keeping time? We'll open that door now, carefully labelled interpretation, and some of it speculative. Interpretations offer different stories for the same score. The Copenhagen tale says the duet is a tool for organising expectations, and that measurement is where the story ends. Many worlds insists every note is played, in parallel halls, with us as the audience dividing at each uncertain bar. Pilot wave theories add a guiding field, a soft current beneath the melody, steering definite particles through a quantum sea. Speculative. Perhaps none of these capture the final stage directions. Perhaps they are lenses, useful, partial, calm. They all agree on the counts we can check: bell violations, no signalling, the statistics of outcomes. Where they differ is in the backstage choreography we can't reach, at least not yet. That divergence need not poison the wonder, it can widen it. For a working musician, the score is what matters. For a working physicist, the predictions. We can push on the boundary, loophole-free tests, cosmic randomizers, delayed choices, and still the duet survives. Interpretation agnostic. If you prefer, keep the image of 2 fiddles whose strings touch only when you ask the right, corresponding questions. The rest is a story about stories, an invitation to think. Yet interpretations can shape curiosity. They nudge us towards certain experiments, certain calculations. They seed ideas we later test, reshape, or retire. We hold them lightly and keep playing. Entanglement has travelled far beyond tabletops. In Austria and China, in the Canary air and over cities at night, photons have stitched arcs of correlation through space. The Mishas satellite sent pairs to ground stations separated by thousands of kilometres. Free space links thread entanglement over mountain ranges and harbours. Fibres carry it beneath pavements, respecting bends and losses with patient repeaters. We test timing like watchmakers. Detectors click within tight windows, closing loopholes where local stories once hid. Random number generators choose angles at the last moment, sometimes seeded by starlight billions of years old. Cosmic light that began before we built the experiment, closing a door on conspiracies. Each advance tightens the hall, hushes the coughs, and asks a sharper question of the duet. There is an everyday wonder here. Cities lit by sodium lamps also carry invisible rehearsals, little pairs leaping across the dark. People look up and think of weather. A lab window glows with photons in lockstep even no human eye could trace. The fabric of our infrastructures now hosts a fabric of correlations, quiet and precise and new. The practical path bends now toward computing. If entanglement is the deep secret source of quantum advantage, how does it help calculation become a symphony rather than a solo? In quantum computing, qubits are strings you can pluck in superposition, but the harmony blooms when those strings are entangled. This shared structure lets algorithms explore patterns collectively. Shor's algorithm braids phases so that factors fall out like a clear chord from a thicket of overtones. Grover's search leans on interference, the softer cousin of entanglement, but scalable advantage typically leans on both. There's nuance. Not every speed-up demands vast global entanglement at every moment. Some tasks need brief, local harmonies, like chamber pieces rather than stadium shows. But take away entanglement entirely and most quantum advantages fade. It's the capacity to establish non-classical correlations, to steer probability flows with coordinated nudges, that makes the difference. Architectures respect this. Superconducting qubits arrange in lattices where neighbours entangle by microwave kisses. Trapped ions form lines where collective motion ties them together. Photonic processors stitch cluster states, vast pre-woven scores you then play by performing measurements in sequence. Across all of them, error correction looms, redundant harmonies that protect the music from hiss at the price of many more strings. We can ask, how much entanglement is enough, and where? The answer is technical and evolving, but the motif holds. Complexity without coordination is noise. With coordination, it's a song. Measuring entanglement requires inference, but sometimes it announces itself by geometry. Cut a material in your mind and ask how entangled the halves are. In many ground states, the answer scales with the cut. That area law tethers complexity to boundary, letting us compress the state into a web of tensors, a score where each edge carries a note of correlation. In one dimension, this yields matrix product states, a kind of linear choir you can write succinctly. In higher dimensions, projected entangled pair states spread the web across surfaces. These representations aren't just maths, they are blueprints for machines and lenses for phases of matter, from spin liquids to high-temperature dreams. Entanglement entropy also peaks into quantum fields and black holes. The vacuum is not empty, it's a fabric of jittering modes, entangled across every cut. Speculative. In gravity, the bookkeeping of this entanglement seems to relate to the area of horizons and the information they hide. The link between geometry and harmony deepens, hinting that space itself could be woven from relations. Even if those grand ideas shift, the practical harvest is real. Compressing quantum states by their boundary complexity lets us simulate materials too large to grasp otherwise, guiding chemists and engineers toward new textures of matter. Entanglement isn't only for computing and keys, it also sharpens our senses. In interferometers, entangled or squeezed light can beat the standard quantum limit, measuring phases more finely than uncorrelated beams allow. Gravitational wave observatories now sip squeezed light to hear the universe murmur more clearly, like pin-dropping the cosmos into a quieter room. Atomic clocks, too, can share entanglement among their atoms to tick more steadily. The collective spin of a cloud is squeezed so that uncertainty huddles in a harmless direction, freeing the measured quantity to ring true. With enough care, such clocks can probe time's flow with breathtaking detail, testing fundamental physics and improving navigation. Even humble sensors benefit. Entangled photons can image with fewer particles, gentle enough for fragile samples. Distributed networks can synchronize by sharing quantum correlations, uniting distant instruments into one coherent ear. The duet turns into a chorus not of volume but of agreement. A question lingers like a held note. Can we push this harmony into the macroscopic world we touch? Mirrors, crystals, tiny drums, and keep it intact long enough to feel. Step into the chill of a dilution fridge, and you'll find macroscopic rhythms. Superconducting circuits, islands of aluminium a hair's breadth wide, carry entanglement across dozens of qubits. In optomechanics, tiny mirrors, human-made and visible, exchange entanglement with light, their vibrations whispering in lockstep. Diamond effects, with spins that can be seen with microscopes, trade quantum notes through the lattice. We've seen Schrödinger's cats in kinder sizes, microwave photons coaxed into states that look like two distinct notes played at once, separated widely in phase space. We entangle those cats and watch them purr in chorus, then fight to keep the room quiet enough that they don't skitter away. The challenge is always the same: hold the hush long enough to play the piece. At larger scales, gravity and heat intrude. That's not mystical, it's mechanical. More atoms, more ways to leak. Still, each year lengthens the leash. We learn to shield, to feed back, to error-correct even the motion of a mirror. The result is not only spectacle, but utility. Sensors that hear fainter ripples, processors that carry longer thoughts. This path meets philosophy at the edge. When you feel a tiny mirror share a quantum with light, the boundary between everyday and exotic thins. The world is one piece. The duet threads through it all. There's a speculative bridge that some physicists explore with care and caveats. If entanglement patterns sketch the geometry of quantum states, could they also sketch space-time? ER equals EPR is a slogan proposing that certain entangled pairs are connected by non-traversable wormholes, Einstein-Rosen bridges, as a way of talking about how information is arranged. Speculative. This does not mean you can climb through a bell pair. The wormhole, if it is more than a metaphor, is sealed to travellers. But the mathematics of entanglement entropies and the areas of minimal surfaces in certain gravitational theories rhyme. It suggests that the fabric we walk on may be stitched from relational threads, with distance emerging from how much harmony ties regions together. Even here, the testable remains our compass. We check how teleportation protocols map onto gravitational stories. We compute how shocks ripple through entanglement in toy universes. These games sharpen both sides, returning us to the lab with new questions. Whether or not the bridge is real, the road it offers pushes imagination and rigor in tandem. If space-time has a backstage, entanglement might be part of its carpentry. Or not. The music stays beautiful either way. Another frontier hums inside living rooms of nature. Birds may navigate by sensing the twists of electron spins in molecules lit by faint starlight. Their chemical reactions sensitive to entanglement length scales within a protein. Photosynthetic complexes might shuttle energy along quantum paths, maintaining coherence over surprising distances and times. Speculative. These hints are under active test, with knock-on effects of noise and temperature that many expect to wash out delicate states. Yet some microenvironments, like shelters within proteins or carefully arranged pigments, can preserve coherence just long enough to be useful. It's a balance, not a miracle, evolution leaning into physics edges when the payoff fits. Even if entanglement plays only cameo roles in biology, the exercise teaches us about robustness. How does warm, wet matter cradle quantum notes? What design tricks can we borrow? We build artificial molecules, shine pulses, and catch transient harmonies before they fade, then feed what we learn back into sensors and materials. The living world reminds us to keep the metaphor modest. Nature doesn't need to be a virtuoso to win. It needs just enough rhythm to make the next move. So what breaks entanglement when it breaks? Imagine drawing a bow across a string while someone taps the bridge. The note jitters, the phase slips. In quantum terms, the environment becomes entangled with your system, and your tidy two-part harmony is now a three-part muddle. trace over the environment, the part you don't control, and the neat correlations smear, different noises gnaw in different ways. Defacing blurs the relative phase between components of your state, a detuning of the internal clock. Amplitude damping drains energy away, as if the string slowly stopped vibrating. Mixed together, they make the world feel rough. But models like these are more than labels. They let us design counter-moves, pulse sequences, dynamical decoupling, error correction. Error correction is the bold stroke, using many imperfect strings to encode a single, protected note. We spread the information across a code space so that local taps can be noticed and reversed. Entanglement is both the problem, what noise steals, and the solution, what codes use. The duet grows into a choir that sings one tone faithfully despite the wind. With these tools, we return to the source. How do we create clean pairs in the first place, and how do we ferry them to where they're needed? Sources of entanglement are instruments in their own right. In nonlinear crystals, a pump photon enters and, with a small probability, splits into two daughter photons whose polarizations or colors are entangled, a process called spontaneous parametric down conversion. The geometry sets the mode structure, the phase matching sets the tempo. We couple the outputs into fibers and guide them where the duet is needed. Atoms and ions, trapped in electromagnetic fields, share entanglement through collective motion. A shared vibrational mode can play courier between spins, letting precise lasers write gates, controlled flips that tie qubits together. Neutral atoms, especially Rydberg states with their enormous sensitive orbits, block one another's excitations, weaving entanglement across optical tweezers in tidy arrays. Superconducting circuits use microwave photons to mediate interactions, with tunable couplers adjusting who talks to whom and for how long. Even mechanical resonators, cooled to near their ground states, can entangle with light or with each other. The palette is rich, the trade-offs varied, brightness versus purity, speed versus coherence, integration versus reach. Each platform is a studio with its own acoustics. Choosing is a matter of the piece you want to play, long-distance keys, fast local rhythms, hybrid ensembles. When Bell first wrote his Inequality, the experiments that could close every escape hatch were distant dreams. Over decades, meticulous work tightened the gaps. The detection loophole, the chance that losses could hide a classical explanation, was addressed with better detectors and brighter sources. The locality loophole, signals sneaking between labs, was closed by spacing stations and timing choices so tightly that light itself couldn't carry a message in time. More recent tests have woven cosmic randomness into the choices of angles, using starlight as a coin toss started eons ago. Others have ensured memory doesn't build across trials. Each step strips away a crutch for skepticism, leaving the simple shape of the quantum curve standing on its own. The duet survives scrutiny. The glove story grows tired. It's here, near the edge of our journey, that we pause and breathe. If you'd like more quiet explorations like this, consider subscribing, and, if you have a moment, share where you're listening from and the time. We've looked outward, but these tests also point inward, reminding us how we know. Assumptions are notes too, candidates for revision. In playing with care, we hear better. Entanglement touches philosophy not as a riddle to solve, but as a practice of attention. It asks us to hold two ideas at once, that parts can be locally random and globally arranged, that influence is not the only route to relationship. It teaches humility about stories and patience with patterns that only emerge in the comparing. For technology, it is a handful of instruments that can do real work, teleport a state, hide a key, sharpen a measurement, bind qubits into engines of calculation. For science, it is a spotlight that reveals the seams of classical concepts and a compass pointing toward new terrain. For awe, it is a reminder that the world's quiet is full of structure. We began with two fiddles slipping off opposite wings, and we end with a whole orchestra, scattered yet coordinated, playing a piece that no single section could hold. The score is not under the stage, it is in the relations, the questions we choose, the care with which we listen. Across distance and doubt, the duet persists. Where in your day could you listen for a harmony that only appears when two separate parts are brought together?